Okay. Now, let's get started. I hope that the people who are on that corner of the class, they can still have the view over here. Or you can just move towards this area. Okay, now, let's get started. Let's, as usual, put the topic. Integration. However, today, guys, Lizzie, please listen. Look at this. Today, now we are going to talk about the integration, but our focus today is more on the geometric interpretation of the integration. Because if you remember, when we said that we talked about the integration, we said that we have two different perspectives. We can make two different interpretations when it comes to integration. The first one that we mentioned, it was this perspective, that we said that we can approach integration analytically, analytical perspective. As a review of that, what did we mean? We said that, imagine that if we have an integration of an arbitrary function as g of x, d of x, which it becomes g capital of the x. Then in the analytic perspective, we said that if the variation happens with respect to the x on the integration, we can say that d over dx of g of x becomes g of x. And essentially that was a kind of an anti-derivative of the function. That was the thing that we have been focusing on that all the way until today. We have an integration. When we find it, it means that the thing that we find is kind of an anti-derivative of this. Because if you take the derivative of the result of the integration, it takes you back to the integrand, something which comes under the integral. And that was the thing we focused so far. And the activity that you are doing, and we are just going to start it again from tonight, which is one integration per day, you are focusing on this. You have an integration, it comes with an integrand, and what do you do by using the substitution is that you find the antiderivative of that function. We have been doing that so far. Now, also, we said that we talked that also in the beginning of the term, we said that besides from the analytic perspective, we have also a geometric perspective. The geometric perspective, the name also speaks for itself. Geometric, it means that you involve some geometry into this. For example, what did we say? We said that, imagine, we have a Cartesian plane. In that Cartesian plane, we have an arbitrary function, which we call that, for example, let's, as I just started with g, we have g of x. Then we said that the same integral, which we talked about that analytically on the left of the screen, we said that we have the same function, small g, which is plotted on the Cartesian plane. And we say that if we can find this between two areas, A and B, that's an interval which the function g of x is continuous. It means that if you start to walk on the surface of this function, there is no hole that you do not fall down. It means that the function is fully continuous between A and B. Then the geometric perspective, what did it say? It says that the integral of the same function, g of x, d of x, because why do we call that d of x? Because we notice that the variation happens with respect to the x. But from the lower limit a to the upper limit b, that in this interval, the function is continuous. We said that. The analytic perspective, it says the antiderivative of this, and that becomes the big capital G. But the geometric perspective says that this integral gives you S of x. What is S of x? It means that the area, let me choose a very good color, this one. It becomes S. It becomes the area under this curve. And that was a geometric interpretation of integration. Then whenever you have an integrand and you have an integration, if you have confined your function between two, can you please close the door? Thanks. And when, thank you very much, Gabrielle. And it means that when you confine it between two limits, between lower limits, lower band and the upper band, which I mean by A and B, which the function is continuous between that, you're essentially finding the area which is between these two parts, the x-axis and the function. And that's why that technically they call that the area under the curve. We have done that also at the beginning of the term, and we had some approximate method to find it. But we do not need those approximate methods because now we know how to analytically solve the integration. Any questions so far? No, everyone is happy? Now, let's move on. This is a review. Let's move on to the new topic that we're going to talk about this today. Now, I'm going to introduce the same thing, but from a little bit different perspective. I'm going to still go back to the same thing that we discussed before I give you one more example. Look at this. How the g of x looked like. This one was like that. Look at this. The same g of x that it was on the previous slide. And we assume that this is going to be the same plot. And also, we take into account, again, we are confined into the same area between A and B, that the g of x is fully continuous. And this is x-axis. Now, I'm done. You have a question? Question? No? And the thing that we want to discuss, again, the same geometric interpretation, but it has a little bit smart trick, which I'm just going to incorporate it into this function. And what is that trick? I say that if I, from the geometric perspective, find this integration from A to B, from g of x, and I know that this is going to be still d of x, because the variation happens with respect to x, and still it gives me the same area, S. What is S? S is the area under the curve. However, and now it's going to be the smart trick, which I'm just going to very smartly incorporate there to use it later. What is that smart trick? Is it possible for an integrand, what is my integrand? G of x. I say that I'm going to subtract it from 0. Does it give me the same result at the end, the same area under the curve? Who says yes? One person. I'm going to say yes. Why? Because imagine that g of x minus 0, for like 2 minus 0, how much does it give you? 2. Then by adding a 0 at there, I haven't done anything almost to that. But what was the reason for it? Why? Why did I do this? What is 0 signifies there? Imagine that if the g of x represents this plot, yes. Fantastic. I love that. Brilliant guess. Brilliant guess. Thanks, Sebastian. What is that 0? This 0, which we incorporated here, and it seems as if nothing happened, it's essentially the equations for the x-axis. What is the equation for the x-axis? It's y equals to 0. Why? Because any point along the x-axis, for example, here, has a corresponding y equals to 0. And that's why you say that y equals to 0 is the line describing the x-axis itself. You have seen that before, huh? Yes? And the same thing for the y-axis, you say the line describing the y-axis is x equal to 0, because any point along it has an x value goes to 0. Now, if that's the case, if y equals to 0 is a line describing, I should say, the x-axis, then I can come here to conclude something very smartly. And we expand on it now to say that the area under the curve is essentially the subtraction of two functions. Maybe g of x represents the function which comes on the top, and 0, which represents the x-axis, is the one which comes beneath the other integral, the other function. If that's the case, it's going to help me a lot. Why? Because imagine this scenario. Imagine this scenario. I'm going to go over there. Where is this one? I'm going to have another scenario. I'm going to call this function h of x. But what is about h of x is this. Look at this. Now I introduce h of x like that. H small of the x. When somebody asks us, imagine two interval from A to B, and somebody tells me, what is the area under the curve? I say, the area under the curve, it becomes here. But it doesn't make sense. And now we run into a problem if the function is reflected with the x-axis, because there is no area underneath that function. But I say, if we incorporate the idea that we developed right now, that we said that what? We said that the area under the curve, it's essentially the integration between these two limits from A, which is a smaller band, goes to the B, of, as what we did before, which involved 0 as the equations for the x-axis. I said that the equation of the first function, which is on the top, minus the equation of the second function, which is underneath. What is the line which is on the top of h of x? X-axis, huh? What is x-axis equation? Y equals to 0, right? Then it becomes y equals to 0. If y equals to 0, I have to put the function 0 minus the function which comes beneath of it, minus h of x, d of x. Now, you say, wait a minute, I have them 0 minus something, it gives me minus of that thing. 0 minus 2 becomes minus 2. Then I can rewrite it like that. Take the negative outside, and it becomes the minus integral of a to b of h of x d of x. You see, we take care of the minus. Then that's why you see that sometimes if the function is beneath the x-axis and you cannot find the area underneath the curve, you get still the integrand, but you introduce one minus behind it. Yes.
When we're trying to integrate into A here.
Yes, still from A to B.
So it's above the curve.
That's right. It becomes above the curve because we introduced this minus sign here.
Okay.
Because there is no underneath. And that's, Tommy's question is very good because it takes us to this very general format that we just want to use the geometric interpretation of the integration. And this is this. Let me choose this one. And this is going to be the main theory of the day. So far, we were warming up. Now we are getting more serious now. This is y-axis. This is x-axis. That's my focus is that we are taking the integration on the Cartesian plane. And imagine that we have function as g of x that we had before. And we introduce another function. I call this h of x. And I say, okay, I'm just going to pinpoint 2 points. For example, from point A to the point, let's say, B. You see that point A and point B, they are crossing both functions. Then I say that, okay, I'm going to find the area which is confined between these two functions from A to B. So far, we did a similar thing. The area underneath the curve was the area between the function g of x and the x-axis. Now imagine x-axis, it becomes its own function. Now we have h of x and g of x. You see the area under the curve, but another curve is g of h of x. Two functions, they cross. Yes. Yes, please. And now we just want to find the area which is confined between them. What happens? The same thing, the same logic. We say S equals the integration from the lower limit to the upper limit, provided that when you walk from A to B, both functions are continuous. It means that it's from A to B. However, we set the rules a couple of minutes ago. We said that first, we write the function which stands above the other one. Between A to B, which function is above the other one? G, the one which is red, which is G. Then I say that it's going to be written as g of x minus the one which comes underneath of it. Which one is the beneath of that? It's the blue one, which is represented by h of x minus h of x times d of x. D of x simply represents that the fact that our variation along A to B happens with respect to x. And that's it. And that's the lesson for today, that the area between two curves is essentially given by the subtraction of those two functions in order of the one which is standing on the top is placed first between these two lower and upper limits, provided that these two functions between A to B are fully continuous. You can expand this one to the area underneath the curve. We did the same thing here. We were finding the area between g of x and the x function, x-axis. And that was the reason that we said that g of x, the one which is on the top, is subtracted minus the one which is on the bottom. The bottom one was the x-axis. Then that's the reason we just put 0 from there times d of x. Then you see that as a result, the area under the curve is nothing, just the area between two graphs. One of them is g of x, the other one is the x-axis itself. Okay, now, any questions? No? Everyone's happy, happy, happy? Yes? Are you tired? Then we give 3 minutes break. You do some stretching, you stand up, do some stretching. After the break, we do solve the problem. Let me also pause the recording. Okay, now we just do one example, then we are done for the day. Okay, now look at this. We have the same thing. We have y, we have x. Now we are just going to have two functions. One function is going to be a quadratic function, which we gave this as y equals to, I'm going to give this as f of x equals to x squared plus x minus 2. And the other one is going to be this function. Which the function is given as g of x equals to x plus 2. Then you see that we have two intersects between these 2 points. Then there are 2 points that these two functions intersect. I call it A, B. It's so easy to find the point of the intersect. You know that if you solve this equation, which we are not going to do that because that's not going to be the purpose of today's lesson. You know that if you just want to find the point of intersect between two functions, simply you solve this equation, f of x equals to g of x, which means that x squared plus x minus 2 should equals to x plus 2. Then you get x squared equals to 4, because x and x here, they are just going to cancel out. You take 2 to the right side, then becomes 4. Then when you solve it, you see that x is plus and minus 2. This means that a starts from minus 2, and you go to the b, which goes to plus 2. These are the point of intersects so far. We ask ourselves, what is the area underneath of the curve between these two curves? You see two functions. They can find between these 2 points, and both of them between minus 2 and plus 2, they are fully continuous. And we ask you, what is the area? The area of the shaded area, which we call it S. Now, we just want to find this. What did we learn? We learned that this is the formula, right? That's what we introduced today. I'm just going to use this in order to find the area. What do? We said that we have to solve this integral, which we know it expands from minus 2 to plus 2. However, we have to incorporate two functions. We are going to subtract the function which is on the above. What function is above? You mean? That's right, the one which is black. G of x minus the one which is beneath of it, which is f of x. And at the end, we know that we have to multiply that to d of x, which represents the variation along the x. Now, what do? We just put the values in there from -2 to +2. G of x is represented by x plus 2. We subtracted off the f of x. F of x is represented by x squared plus x minus 2. And all of them, we know that it just varies with respect to the x. That's why we just put d of x here. Now, we continue from there. -2 to +2. We simplify whatever is as an integrand. We have x plus 2 minus x squared minus x plus 2, d of x. You see that obviously this x here cancels out with this x. Then what are left at the end is this integration of -2 to +2. What we have 2 plus 2 becomes 4. 4 minus x squared d of x. Now, in order to solve it, what do? We say that, okay, how to solve this? This becomes very simple. Now we are on the analytic verge to solve this integration. To solve them, we do not need to do the substitution even though, because we learned this identity, that this identity said that if you have the integral of x to the power n d of x, it's essentially the antiderivative is given by this expression. We can also say plus a constant, but it doesn't matter to include it. Now, if that's the case, I'm going to do one by one here. We have two terms to use that integration. One is 4, and the other one is x squared. The integration of 4 becomes how much? 4x, using this identity. You see that if you take the derivative with respect to x of 4x, you get back to the 4. Then we are right. The integration of the x squared becomes x cubed over 3. We take the derivative from x cubed over 3, we see that it becomes x squared. Now we are correct. Now, because looking at it from the upper and the lower limits on the x-axis, we notice that we normally do this. We put -2 plus 2 here. Now we have to put the numerical values in there to find it. Then it becomes, we first substitute 2 inside the expression. Then as a result becomes 4 times plus 2 minus plus 2 to the power 3 over 3 minus, we put -2 right now into this expression because 4 times -2 minus -2 to the power 3 over 3. Yes, Tommy? 4x. Look at this. 4x is a result of integration of 4. Look at this. Integration of 4 d of x becomes 4x. Why? Because we had this identity, x to the power n d of x becomes x to the power n plus 1 over n plus 1. Then if we have 4 here, integration of 4 d of x, it's essentially is 4 times x to the power 0. Correct, Tony?
Yeah.
Then as a result, when you look at the identity on the top, you can take 4 outside. You remember that, huh?
Oh.
It becomes 4 integral of x to the power 0 d of x becomes 4. And now look at this part. This part essentially is this identity.
Okay.
The n is 0, then it becomes x to the power 0 plus 1, 0 plus 1 becomes 4x.
Okay. Thank you.
No problem. Now, the rest of the case is a very simple using the calculators to find the rest. We have 4 times 2 becomes 8. We have minus 8 divided by 3. We have 4 times minus 2 becomes minus 8. Minus 8 becomes plus 8. And we have also minus 8 minus 3 becomes plus 8 over 3. Oh, yes, that's, I was saying that, okay, it's going to be very easy. Thanks for correcting me. It becomes minus 8 over 3. Becomes minus 8 divided by 3. Minus becomes plus, then it's minus over there. Then it becomes, at the end, 16 minus, then we get 16 over 3. Then the rest also becomes, I have no space to write. Let me choose the color. 48 minus 16 becomes 38. 38 divided by 2. I have nowhere to write it. I think it's okay. We just stop there. No need to write that precise value at me. But the purpose was that to show them how the method works. Any questions? Everyone's happy? Now, I'm just gonna today. Let me, Dom, Dom is already gone. Okay, let me save it. And let me stop the share. And also let me stop the recording.